Hello students, in this video, so this is the last part of our second order equations, and this part we will call it as a heat equation, right? So the equation which we are interested in looks like this: ut minus Laplacian u equals to 0. Clear? So this is, of course, this is in some domain. Yes, I will explain to you again what the domain is. So maybe in some domain, let's just say, okay, let's not put in whatever. This is the equation essentially, okay? And this is called the homogeneous equation, right? This is called the homogeneous equation. Okay. And of course, if you replace u or 0 with f, so let's say also if ut minus Laplacian of u equals to f, then this too is called a non-homogeneous heat equation. Yeah, but the thing is, to study homogeneous heat equation, a non-homogeneous heat equation, we need to know how homogeneous works, right? Okay, so now let us understand. So there are some conditions here. This problem is subjected to some initial and boundary conditions. Initial and boundary conditions. I will put everything into context once I get going. For now, let's just assume there are some conditions. Okay. Exactly like wave equation, we put some condition. Here also we'll put some condition. Yeah. Okay. Now what is u here? Let's understand this. See the time. There are two variables here. One variable. So let's see variables. There is a variable t. So t is your time variable. Yeah. So we will assume t to be always positive. We assume time to always move forward, right? So t is greater than or equal to 0. Now that Laplacian of u, what does that mean? So you see, in this case, that Laplacian is with respect to the x variable. Yeah. See, u is a function of x and t. Is it okay? And this x, so Laplacian of u x, this we write it as Laplacian of u. Clear? So here you see, although u is a function of x and t, this Laplacian is essentially nothing but u x1 plus u x2 plus u xn. Is it okay? And you can see that there is no t variable involved in here, right? So it is only just second order derivative with respect to the space variable x. This is an n-dimensional heat equation, of course, and you can talk about the one-dimensional. So see, 1D heat equation, how does it look like? You remember we talked about 1D wave equation. This is 1D heat equation. So it will look like, essentially, one dimension means the space variable is one dimension. So you have this sort of problem: ut minus u xx equals to 0. So here t is greater than or equal to 0 and x will be in some domain. For now, let's just assume it to be R. X can be in some bounded domain also. Absolutely no issues. See, the thing is that depends on the problem, but essentially that's the equation which is interesting. Of course, depending on the domain, the solution changes, but there will be some domain where all of this is defined. That's the point. Okay, right. So here, see, in this problem, in 1 and 2, what happens is this: the t is assumed to be positive. Of course, it is greater than or equal to 0. That's not the point. At t equals to 0, you will be given some conditions, right? Initial conditions, remember. So generally, t equals to t greater than 0, and x will assume it to be from domain omega here. And what is omega? Where omega subset of Rn is open. Rn is open. Is it okay? See, here I am doing it for Rn. If you think of it, you can think of it as a R also. So in this case, omega, you think of it as a subset of R, which is, let's say, some interval AB. You can think of it as some interval AB. Yeah. Okay. So in that case, it will be a one-dimensional heat equation. Is it okay? What is u? Here, u is from omega bar. Here, omega bar is omega union the boundary of omega. So omega bar is what? It is omega union the boundary. Yes, omega bar. So close 0 infinity to R. Is it okay? So this is your u, and see, so essentially you think of it like this: u is a function of x and t, right? Yes, x is coming from here, t is coming from here, x and t. Yes, and as I have already explained, the Laplacian is taken with respect to x. Taken with respect to x. Is it okay? So there is no t variable involved in the Laplacian part of it. Clear? And what is f? And f is also given from omega cross 0 infinity to R. Clear? That is f. So essentially in 2 basically we have f, so that is given. Clear? So that is the whole format of it. What is it? The equation looks like ut minus Laplacian equals to 0. Yeah. If you compare this equation with your canonical form, so if you compare it, we have that this is a small note that 1 is parabolic. It's a parabolic equation. Huh? Please check this part. It is very easy to check. Check it. It is a parabolic equation. So basically, we talked about first of all Laplace equation, which is a prototype for a what is it? Elliptic equation, right? Elliptic equation. And then we have wave equation, which is a prototype of a hyperbolic equation. Hyperbolic equation. And then we have what is it? Heat equation, right? Heat equation, which is a prototype of parabolic equation. So what is parabolic? B square minus 4ac is 0. That's parabolic. You can easily check that this is true. Okay, right. So since these are the prototype things, so we need to know how to handle these equations. Yes. Okay. So let's understand the physical interpretation of why this is true. Now, I must say that this heat equation is actually the most important equation. I mean, if you think about it, I mean, the study of heat equation is one of the fundamental objects that humankind has done. Why? I will tell you. Because the thing is, since heat equation, so Fourier initially started studying this heat equation rigorously. And from there, he actually developed something called a Fourier series, which actually, so it is called Fourier series, which we already did, right? So Fourier series is developed by Fourier, Joseph Fourier, while studying heat equation. He wanted to study good heat equation, and then he introduced this thing. And then, and as you know, that today most of these things, I mean, starting from semiconductors to this biology, so essentially medical equipments, all these things depend somehow, the mathematics behind it uses some sort of Fourier, transform or Fourier series, right? So it is very, very important. Physical interpretation. So let's start with the physical interpretation of the heat equation. Okay. So what we have is this. See, the heat equation is also called diffusion equation. Basically, it is a evolution equation. What is it? Evolution. So it evolves with time. It evolves with time, right? So why? Because see, in wave, if you look at the Laplace equation, Laplacian of u equals to 0. So let's say in 2 dimension it is uxx plus uyy, right? Uyy equals to, let's say, 0. See, there is no time variable involved. So essentially, it does not change with time. That's the point, right? So it does not depend on the time. The state is a steady state. Steady state means with time, the state does not change. It only depends on x and y. Okay. Now you see, look at this equation, utt minus uxx equals to 0. It's a one-dimensional wave equation. But for this equation, you know that this t variable, t dependence is there. So what does that mean? It means that the equation depends on the time variable t. Okay. Now, similarly, you also have this equation, which is ut minus uxx equals to 0. So it is one-dimensional heat equation. Here also you see the ut part is there. So basically, we are actually trying to model something which changes with time. So that is called, it is evolve with time, right? It changes with time, evolves with time. Okay. Now the thing is this. So let's say that let a subset V, V subset of omega, okay, is a smooth subregion. Smooth subregion, okay, region. Then the rate of, we know this thing, right? The rate of change of the total quantity, change of total heat in the system, you can think of it, okay, heat. So basically we are somehow modeling heat, right? So this can model heat, this can model chemical concentration, all of these sort of things, right? Okay. So the total change, the rate of change of total heat, okay, in a system within V, system within V, okay, equals the negative of the net flux through del V. Net flux through del V. Okay, what does it means? So basically, if let's say that let's think of it as a room, right? Now the thing is this, if you want to find out how much heat is actually, I mean, uh, how is the room temperature changing? Yes, that will depend on how much heat is flowing in or out of the room, right? So essentially that is the whole thing. So here also it is saying that if you take a small region V, whatever, what is the net influx of it around from the boundary, that actually determines what is the total change in the system. That's the point, right? Okay, so if F is the flux density, if F is the flux density, okay, then d dt of integral of v u dx. Okay, why this is true? See, integral of v u dx is what? It is nothing but the amount of this rate of change of total heat in the system. Is it okay? Yes, so you can think of u as the temperature at some point on the system in v. Clear? Okay, so integral over V is the total, I mean, how much heat is there, you can think of it like this. And then del T of that is essentially the rate of change with respect to time. Yeah, okay, within V. Now that is equals to the negative of the net flux. So flux density is F, so it is F dot gamma ds. That is basically your the net flux through the boundary del V. Is it okay? Yeah. Okay, now you see, since this V is arbitrary, therefore you can take this T inside, right? Because this you see, this the system V, sorry, what am I saying? Yeah, see this domain V, sorry, the integral is on with respect to x, right? The integral is with respect to x. This V is in the variable x. So essentially, omega is in the x variable. Think of it like this. Maybe I can draw it here. So this is your omega. Is it okay? And there is this time variable here. Time variable. So this is the whole domain, the cylinder, right? Now you see this omega v is somewhere here. Now the integral is with respect to x, which is in v. So if I'm taking the derivative with respect to t, I can take it inside, right? The derivative with respect to t does not depend on v. Yes. Okay. So that means that will imply that integral over v ut dv, yeah, this is equals to minus the integral over v divergence of f dv. Yeah, this is Gauss divergence theorem. Clear? Okay, so if this is true, then that will imply ut equals to minus divergence of f, right? Oh, sorry, minus divergence of f, right? Now, since v is arbitrary, so basically this can hold for any v, so that is why this is true, right? Now generally what happens is this, see, generally this f, this vector field f, that is the flux density, right? That flux density is proportional to the gradient of u, right? Gradient of u. So what points in the opposite direction, but points in the opposite direction. Yes, what does it mean? I will tell you. Point in the opposite direction. So this means that, see, the flow, if you look at it, it actually goes not from lower to higher, but from higher to lower. So you see, flow moves from higher to lower, right? So that is why this negative direction is there. Okay, so if you substitute this f. Okay, so essentially what is f? F is proportional to gradient of u. So this is basically nothing but minus constant times gradient of u. Okay, so this a is positive. Is it okay? Now, if you substitute that in this equation, therefore what you get is ut equals to minus divergence of a times divergence of gradient of u. So which is nothing but that will give you ut equals to a Laplacian of u. Is it okay? And of course, when equals to 1, you have this heat equation. Doesn't have to be a equals to 1. You can make a change of variable and you can reduce it to the heat equation. So basically, you have this in omega, right? So this is valid for all v. And since this is valid for all v, you can just say that this is also valid for omega. Is it okay? So this is the idea. Generally, what happens is this: you want to, somehow calculate what is the heat flow through a system. Yeah, and that is what it does. I mean, in the physical interpretation. Okay, now what I will do is this corresponding to Laplacian. If you remember, we talked about something called a fundamental solution, right? Here also we will define something called a fundamental solution. For Laplacian, we have derived it. Here we are not going to derive it because it's a little complicated than Laplacian, okay? And that is not part of your syllabus. So for now, we will just define the fundamental solution for the heat equation. Fundamental solution. Okay, what is it? Fundamental solution. Okay, definition of fundamental solution. Okay, let's just write it. See, we will write it as phi of xt. Yeah, and it will look exactly like this Laplacian only, a little change. 1 by 4 pi t to the power n by 2. Okay, and then e power minus mod x square by 4t. And this is x is in R n and t greater than 0. Is it okay? And 0 if x is in Rn and t negative. Yeah. So this is called the fundamental solution of the heat equation. Okay. Now, so this is very important. Why? Because you can use fundamental solution to actually deduce the solution for an inhomogeneous problem. Let me go through that. So it's called the fundamental solution of the heat equation. Heat equation. Okay. Now the thing is this, let's say that we'll put some initial conditions and we want to solve this problem. So let's try and find a solution for the initial value problem. Okay. So you see, initial value problem, value problem. See here, what I am going to do is, you see, separation of variable and all of this can be done. Of course, that can be done. Yes, that is not the point here. Yes, we will do separation of variable, but this is a small, result which I want you to know, and this actually guarantees that there is always a solution. Separation of variable may or may not be used all the time, but this is just a guarantee that there is always a solution. That separation of variable gives you a explicit solution. Yes. Okay. So initial value problem. What is the initial value problem? So the Cauchy problem looks like this: ut minus Laplacian of u equals to 0 in Rn cross 0 infinity. Yes. So x is in Rn and this time variable is 0 infinity. And what is on the initial at t equals to 0? So at t equals to 0, u equals to g on Rn cross t equals to 0. Is it okay? Now the thing is this: if this is given to you, then the solution of this problem will look like this. The proof of this we will not do. The proof is not is omitted. Because you need a lot of different theory to prove this, which is beyond the scope of this syllabus. I just want you to know that this can be done like this. I will show you a different method of explicitly solving it, but why fundamental solution is important? Because we can do this. Yeah, so you see, u of xt can be written like this: integral of Rn. If you know convolution, so basically we are going to do something along the same line. It is phi of x minus y times t g of y dy. Is it okay? See, this is g of y. We are taking this into account, g of y dy, and then that will be your. So essentially, what happens is this is basically your solution here. If g is bounded, so then this is a solution of 2 if g is bounded. Is it okay? I hope this is clear. Provided g is bounded, this is a bounded continuous, bounded and continuous in Rn. Continuous in Rn. Is it okay? So with boundedness and continuity, you can actually show that this is the solution. Yeah. Again, I am not proving this in any way. Okay. Now with this thing, of course, there is another small thing which we need to know here. This is called the infinite propagation speed. Infinite speed of propagation, we say. Speed of propagation. Okay. What does it mean? It means that this is called physically infinite speed of propagation. What it means is this: see, if g is bounded and continuous, okay, and G is greater than equals 0, G not equals to 0, not equals to 0, then u of xt equals to 1 by 4 pi t to the power n by 2, okay, integral over Rn. We already know this, right? This is the fundamental solution, x minus y square by 4t g of y dy. Yeah, fundamental solution. See, yes. Now you see, phi. I'm just writing it down. This is phi. I'm just writing it down. Now you see, if g is positive, this is always a positive term. So essentially, the whole u is positive, right? Then this is positive. U is positive essentially. U is positive for all x in Rn, right? Whatever x you choose, this is always going to be positive, and t positive, and t in R. So basically, if you choose any x in Rn and any t positive, then u of xt will be positive provided g is non-negative. Clear? Yeah, this is always true. Okay, and how do you interpret it? So interpretation is this. Interpretation. This is why I wrote the formula down. So interpretation of it is this. See, it says that if you have a disturbance, right? So you see the heat equation, you can put it this way, the heat equation, okay, forces infinite speed of propagation, ISP, yeah, infinite speed of propagation for disturbances. This is what we say, disturbances. Okay, what does it mean? It means that if the initial temperature, see, this is nothing but the initial temperature, U is the temperature, right? So if this the initial temperature G, if this is positive, is it okay? Then so basically this says that if the initial temperature, see, G is initial temperature, if the initial temperature, so basically at the time t equals to 0, temperature, okay, is non-negative, G is non-negative, okay. So basically you think of it like this, you have a system and the initial temperature at t equals to 0, the temperature is non-negative, so basically not 0, let's just assume. This says that the temperature at any later time will actually remain positive, non-negative, then the temperature at any later time, okay, so it can be very small, doesn't matter, is everywhere positive, is it okay, everywhere positive. Okay, so this is called infinite speed of propagation. You can actually find out that the wave equation that actually has a finite speed of propagation. This is infinite. Yeah. So for this sort of equation, wave equation is basically behaves differently than heat equation. Heat equation, once G is positive, the initial temperature is positive, it remains positive for all time t and for any region point x. But the thing is, in wave equation, this does not, hold. You can actually try and prove this thing. Yeah. But the thing is this, I hope this is clear at least. Okay. Now, the thing is, we want to prove something, and the proof of this particular theorem is a little complicated. What we will do is maybe, okay, let me tell you a little more about initial propagation speed. So let's say that, let us do it again. This is 1, this is 2. So let's look at this thing, that okay, maybe I can first of all prove the Maxwell principle, not prove it, I will just write it down, the Maxwell principle, and then I will tell you what that initial speed of propagation is. So strong Maxwell principle, strong maximum principle. Okay, you remember we talked about Maxwell principle for harmonic equations, and we proved that it can only be attained on the boundary. If it attains in the interior, it will be constant, right? Here also similar sort of thing happens. The proof is definitely not for this course. It is a little complicated than that. What I will do here is, of course, a very simple proof. So let me give you an idea of why this is true. Let's say that ut minus Laplacian of u equals to 0. Is it okay? Yeah. And this is in some domain. Yeah? Let's just say this is in some bounded domain, and the domain for now is, let's say, closed AB, sorry, in uh, omega bar, right? So it is closed AB cross 0 capital T. Huh? Okay. And some boundary condition is there. So in the boundary, so let's say here, this is x, right? X is between A and B, and T is between 0 and capital T. So essentially, this is the place, this is the room where we are interested in. Clear? Now, what this is saying is this, see, if you think about it, if let's say this room has some temperature, right? So basically there is this heat distribution within the room, and let's say there is a AC which is working here, right? So near the point, near the AC points, the temperature will be, and let's say the AC is working, right? So near the temperature points near the AC, the air will be much cooler than far away, right? And the thing is this, so if the maximum of the temperature, if you want to find it where it is the hottest, then it will be the farthest away from this AC. So basically wall. So if the heat, think of it like this, if the heat is actually coming in or going out from the wall, the maximum and the minimum of the heat distribution should be on the either, of course, on the sides, right? So basically on the boundary. It can't be in the middle. Yes. Okay, the maximum will be attained somewhere which is farthest away from that point. So that will be on the boundary point. And again, the minimum will also be attained very closest to the source where cool air is blowing, right? You understand? That's the idea. Okay, so the proof, I will give you the proper statement. I will just give you an idea of why this works. But the statement, this statement which I am doing, the proof of it is not included. Yes. Okay. So let's say that, and let's just take, this is Laplacian, not Laplacian. In one dimension, I am doing uxx. Yeah. Okay. So let us say that the maximum is attained on the, in the interior. Yeah. Let's just assume it is attained in the interior. So u at the point x naught and t naught is a interior point here, and let's say there is this maximum of u. Clear? Let's just call that be m. Yeah. Okay. So in this point, if the maximum is attained, it means that the gradient of u, gradient with respect to u. So basically it means that ux and ux at the point x naught t naught and ut at the point x naught t naught is definitely going to be 0, right? So basically this is a critical point, x naught critical value. So x naught t naught is a critical point in this case. Okay. So that will imply that ut at the point x naught t naught, this is 0. Clear? So essentially this, what happens to this equation, ut minus uxx restricted to x dot t naught. Let's just understand this. See, this term is gone because ut at the point x naught t naught is 0. What about to uxx at the point x naught t naught? Okay, let's just understand this thing. Okay, at the point x naught t naught, u has a maximum. So the Hessian of u, d2u at the point x naught t naught, okay, this should be negative definite, right? Okay, it should be less than equals to 0, but you can actually take a change of variable with, I mean, you can modify the function and do this. Yeah, let's just understand that if it is strictly negative, so if the Hessian matrix is negative definite, strictly negative definite, then what happens? Then we have x transpose, this Hessian times x is negative, right? Now, if you take x to be 0, 1, 1, 0, sorry, then you see that this becomes uxx, and then uxx becomes negative. Yeah. So if uxx is negative at the point x naught t naught, then this is negative. So negative minus negative is positive. So this term will be positive. But you are saying that this is 0 for all points here. So that's a contradiction. So you understand that the maximum cannot be attained in the interior until unless it is a constant. Is it okay? Right. So what do you have is the strong maximal principle. So assume u is in C2, so twice continuously differentiable in the x variable, once continuously differentiable in the t variable. Is it okay? And then it is omega cross 0t. Yes. Intersection C of maybe I can use a small notation because otherwise this is getting confusing. Okay, so what I will do is this, maybe let's do this first. First of all, we'll define something called a parabolic cylinder. Parabolic cylinder. Okay, what is a parabolic cylinder? It is nothing but we will define omega t. Omega t is omega cross open 0 t closed. Okay, so what is it? So let's say that you have this domain, right? This is your x variable, x and y. This is your space variable, space, and this is your time variable, t. Now you see, corresponding to this, you have this region. You have this region. So this is a cylinder where we are working with. This is a cylinder. Okay. Now you see, this is your time t equals to 0. That's your omega, time t equals to 0. Okay. Now omega t, this is defined as omega cross 0 t. So basically this cylinder, yes, and the parabolic boundary is this parabolic boundary. Now you understand the parabolic cylinder, right? You see, it contains every point inside and the product of this with open 0 t closed. Clear? So every point on the top of this cap also, those points are there, but the boundary points are not there. These boundary points, these are not there. Okay, except that everywhere it is there, and also the cap part is also there in the parabolic cylinder. Okay, so what is the parabolic boundary? Parabolic boundary is given by gamma t, which is defined as omega t bar. Omega t bar is the whole cylinder. So basically the top, the bottom, the boundary, everything, minus omega t. Minus omega t means minus this particular part. So basically what happens is this part contains this cap, right? This cap upper top half. So this does not contain the top half. This does not contain whatever is the interior. So this will contain every point on the boundary of this omega, which is t for t equals to 0, and then every other point on the lateral side. You understand? So think of it like a tin. The top part of the tin is not there, and except that everywhere the base part is there and the boundary is there. That's the parabolic boundary. Okay, so the cap is not there. Think of it like this: the cap part is not there, except that everywhere everything is there, but not the inside. Yeah, just the boundary. That's the parabolic boundary. Okay. So once that is clear, we will define something called a strong maximal principle. So this is strong maximal principle. Yeah? Again, the proof will not do. Right. So let's say U is in C2 1 omega t. C2 1 means twice with respect to x variable, space variable, once with respect to the time variable t. Yeah. Why? Because you see ut minus uxx equals to 0. So we want it to be once continuously differentiable with respect to t and twice continuously differentiable with respect to x. So that is why C2 1. Clear? Intersection C omega t bar. Omega t bar means up to the, so everything within the whole tin, the boundary, the cap, the top, the base, whatever is inside, everything, it has to be continuous. So let's say if U solves the heat equation, U solves 1. Here in omega t here, yeah, in this domain. Okay, right. Then two things happen. Maximum of U, as I have explained to you, the maximum of U, that will be definitely attained. Why? Because U is a continuous function on a closed and bounded set. So the maximum is attained. But where will it attain? I just showed you what a one-dimensional thing. It will be always attained on the boundary until unless it is constant. Okay. So it is attained on the boundary. Maximum of U over omega t bar is nothing but maximum of U over gamma t. Okay. Gamma t. Okay. And B, C, as I told you, that if the maximum is attained in the interior, then it has to be constant. If maximum of U in omega t bar is attained at U of x naught t naught, where x naught t naught is not in the parabolic boundary. Okay, x naught t naught is in omega t. Yeah, then it is constant. U is constant in omega t naught bar. Is it okay? Yeah. So that's the maximal principle. So basically you can replace maximum with minimum and still it holds. So idea in one dimension is clear. we can do it for higher dimension also, but to do something for like this in higher dimension, we need something called a maximal principle, which we really don't know. And please note here one thing very important: we are taking the bounded domain to be bounded. So omega is open bounded, bounded and connected. This is important. Connected means, as I told you, any 2 points you can connect it. That's the idea. Okay. So with this, what we have is this. We can actually use this to prove something called a uniqueness. Uniqueness on bounded domains. On bounded domains. So what does this theorem say? It says that if you have this equation ut minus Laplacian u equals to f in omega t and u equals to g on gamma t. Here, if this is the case, then u, if you are looking for u which is c1 of omega t intersection c omega bar. So basically it is continuous in the whole team, and it is twice continuously differentiable with respect to x, once continuously differentiable with respect to t in the interior with the cap. So if that happens, then this solution is unique. Yeah. So there is exactly one solution of this problem. Let's just call it 4. There is exactly one solution here. How do you show that? This you have to do it yourself. Okay, I will give you some ideas. See, if there are two solutions, u and u tilde, then define w to be u minus u tilde. So u and u tilde is in this space. So u minus u tilde are in this space means w is also in this space. Okay, if w is in this space, then w satisfies this equation. You see, wt minus Laplacian of w equals to 0 and w equals to z on the parabolic cylinder in omega t. Okay, so if this is true, then okay, I told you to do it yourself. I am doing it myself. Now you can do it, right? I think use strong maximal principle. See, if this is true, so sorry, w equals to g 0, right? So wt minus Laplacian w satisfies the heat equation, right? So equals to 0. So w satisfies the heat equation and w is 0 on the boundary. So what does that say? It says that the maximum and the minimum is attained on the boundary. You see, maximum and the minimum will be attained on the boundary. So if the maximum and the minimum is attained on the boundary, what are the maximum and minimum? That is 0. So basically w is 0 everywhere. Is it okay? So basically it says that u is equals to u tilde. Already I did it. Now the thing is this, a small note. Okay, this theorem does not hold the strong maximal principle. Maybe I can write it this way: the maximum principle, strong maximal principle, does not hold. Where is it? In Rn cross 0 infinity. There is a maximal principle in this domain, but not in this form exactly. You need some type of growth condition on you, without additional assumption on you. Okay, you understand? So it does not hold assumption on you. Is it okay? Okay, so basically, and the thing is, what about uniqueness? Uniqueness also does not really hold. Okay, so essentially, there is another small note which I want you to know. This is very, very important. See, ut minus Laplacian of u equals to 0. In Rn cross 0 t, and let's say u equals to 0 on Rn cross t equals to 0. Okay, this problem, you can see that of course u is equals to 0 is always a solution. Okay. Now there are other solutions. There are infinitely many solutions, and one can show there exist infinitely many solutions. Okay. We will talk about how to find solutions and all, but in the next class. This class, essentially, we are just talking about properties of the function solutions. Okay, so please understand this thing. If your domain is bounded, right, the space variable where x is varying, if that is bounded, closed bounded set, of course, no issues. Maximal principle holds, uniqueness holds, everything is true. But if it is not bounded domain, so it is in Rn, then the strong maximal principle does not hold without additional assumptions on U, and similarly the uniqueness also does not hold. Is it okay? So I mean, big changes. Okay, so with this I am going to end this video, and in the next video we are going to talk about separation of variable and how to use it to solve the heat equation. Thank you.